So welcome everyone to the first technical part of that course here. We're going to dive into concepts that we use in robotics, and this is a short primer on probability theory, really on a very, very basic level, just introducing you to a few, let's say, rules that we are using. And based on those rules, we also will do the first thing today to derive the recursive Bayes filter, which is a framework for state estimation. So in order to estimate the current state of a system, for example, the position of a mobile robot in the environment, based on sensor data and based on control commands that are, for example, the steering commands of that platform. And we can do this just from starting from the very, very basics, and within a few minutes can derive the framework for this recursive Bayes filtering, which then can have different realizations such as the Kalman filter or the particle filter. And we're going to start with that. So these probabilistic techniques are often used in robotics. So whenever we have systems which need to navigate through the environment, which perceive the environment with sensors and derive actions from that, those systems typically need to work with probabilities because they do not know exactly in which state they are in. They only can estimate where they are. And this is best done with probabilistic approaches because it allows us to explicitly encode uncertainty. And we can take this uncertainty also in decision-making processes into account in order to be more robust with respect to noise. And our world is always noisy. We never live in the perfect world. So several techniques are relevant here in robotics. This starts with general state estimation, and then we have, let's say, common applications of the state estimation techniques. This can be mapping, so estimating what the world looks like, as well as localization, means estimating where we are in the world. We can also solve both of the things jointly, which is then called simultaneous localization and mapping, or SLAM. This is something which will happen more towards the end or in the second part of this course, that we explicitly dive into the simultaneous localization and mapping problem. But you should already in this course get an idea on what the problem about that is. And then we ask ourselves, how can we navigate through the environment? And that's something which typically involves motion planning. So planning which action to execute in order to reach a goal or come closer to a goal, and then also using controls in order to execute these high-level motions that are executed. We start with state estimation. So state estimation in robotics often refers to things somewhere in space. So very often we need to estimate geometry, and that means we need to estimate where is an obstacle, where is a landmark, where is a platform. Some things may be dynamic, such as the platform moving through the environment or this car driving through the environment. But there are certain things in the environment which are static. For example, trees in the environment are at least rather static, or lane markings on the road, or traffic signs. And we want to estimate the location of those things, those objects, for example, in order to build a map of the environment. So a lot of those state estimation problems involve estimating where the system is, so where am I, and what does the world look like. And those two problems are coupled with each other. You can envision this if you see, for example, a street sign 20 meters in front of you. It depends where you are so that you know where this street sign actually is. And also the other way around, if you don't know where you are, but you have a map of the environment and you see a street sign, or let's say a distinct street sign, you can estimate where you are given that you see it and you know where it is located based on your map information. So there's a coupling between the question, where am I, and what does the environment looks like. And this is something which can be seen as localization and mapping, or if you solve that jointly, what's called the simultaneous localization and mapping problem. And so this is an example of a 3D model built here with exactly the vehicle you have seen before. When you have a vehicle which is equipped with a 3D LiDAR scanner, so can estimate the distance to obstacles, to objects, basically, which reflect the LiDAR beam and then gives you range information, how far that object is away. And by estimating the pose of the platform, so actually driving around here and integrating this these range information combined with the positional information, you can actually build a 3D model of the environment, at least a 3D point cloud, in order to use this information then to localize, navigate, or do other things. So this is one example where you have a combined localization and mapping task that you need to solve. Okay, so why probabilities? Why are probabilities important here? The key reason for this is that the world is noisy. So we will never get perfect observations, and we will never exactly execute what we want to execute. So we have uncertainty in the motion execution, and we have noise or uncertainty in our observations. There is no perfect sensor. There is no perfect platform which does exactly what I tell that platform. And so those things are affected by noise and uncertainty. And so the best thing is to take that uncertainty into account in our model, and to take this uncertainty explicitly into account in state estimation, and even in motion execution, by taking into account how certain I am about, let's say, certain variables in my model, so that I can take that uncertainty into account in order to select the appropriate action. We can see this in a very simple form with the localization problem. So traditionally, a system may say, the robot is exactly here. So the robot is precisely here at that X location. So if the system is just, let's say, 5 millimeters off from that location, that's wrong, and maybe can lead to catastrophic failures if you just pass by an obstacle with a security distance of 3 millimeters. This can be bad. So a better approach is to use a probability distribution that says the system or the robot is somewhere here. I do not know where it exactly is, but I know roughly where it is, and I can estimate the probability that the system is in a certain region. And if I take that uncertainty of the platform into account, I may increase my safety distance to obstacles, for example, or generate actions that avoid collisions or reduce the probability of collisions towards zero. And that's something that I can do if I have that information. But in order to have that information, how certain I am where the platform is, I need to dive into probabilistic approaches. So I need to take probabilities into account, and especially in my probabilistic model, in order to estimate what the state of the system is and what the world looks like. And therefore, we need that. Okay, so let's start with a basic primer on probability theory. Again, this is not a theoretical course. This is just, let's say, half an hour wrap-up of key concepts that we will be using here. So, as I said before, probabilities are a key tool for realizing robust state estimation, not just in robotics, also in any other discipline where you work with real-world data. And the advantage is that the probability theory allows us to explicitly model uncertainties. And explicitly modeling uncertainties make the mathematical model more complex, but also more robust, because we cannot expect the system to be exactly in one state. And if I look to the techniques that we consider here in that course, I would roughly say 90% of the techniques that we are going to present here are based on probability theory. So it's important for you to get comfortable with probability theory and that you're able to do basic manipulations. If you look into probability theory, it turns out that it is actually based on a small number of axioms. So axioms are definitions, and based on these definitions, everything else can be derived. And so, for example, in this example, PR of A denotes the probability that a proposition A is true. So P of A means what's the probability that A is true. And we have 4 definitions for this statement. So the first definition that we use, the first axiom, is that the probability is always a value between 0 and 1. So it can't be negative, it can't be larger than 1. So it's a real number between 0 and 1. And the probability of the true event, so something which holds, is 1. And the probability for false, so for something which does not hold, is 0. So probability of 0 means that is not the case. Probability of 1 means this is exactly the case. Probability of 0.5, so value in between, could mean, yeah, in 50% of the cases it holds, in 50% of the cases it doesn't hold. Okay? So, and then we have, if you have 2 propositions, A and B, the probability that A or B is the case, or holds, is equal to the probability that A holds plus the probability that B holds minus the probability that A and B hold together. So this is an OR and this is an AND. So that means A or B, and this means A and B is true. Okay, so this means the probability that A or B is true means either A is true, that's fine, or B is true, That's fine. These are those two probabilities over here. And then we need to subtract something, because the event that A and B hold, we have basically counted twice in here. So it needs to be subtracted once. And these are the four definitions, the four axioms on which everything else is based upon. So we can also look to this last axiom over here and visualize it. So if this is kind of the whole space of true events, and blue refers to A, and B the yellow refers to B, then that A or B holds is basically this area over here. It can be visualized by this area, spanning either A is true or B is true. But if you count the area of A and the area of B, this area in the middle here you have actually counted twice. This is the area that A and B holds. And therefore we have to subtract it once in order to actually get that area over here. And this is basically a visualization of this axiom over here. And basically we can start from those axioms and derive everything else from those axioms. So for example, just as kind of one small example, we want to derive what does the negation of A means, so not A. So what is the probability of not A? And now we want to use those axioms to derive what not A actually means in terms of probabilities. Okay, so we can start with using the last axiom and use instead of B, not A. Okay, so it's the proposition that A is false. So that means the probability of A or not A is, just applying the axiom, the probability of A plus the probability of not A minus the probability of A and not A. Okay, so now let's get a step further and combine certain things in here. So what does it mean, the probability of that A is true and that A is not true? So the probability that A is true and A is false. You can clearly see that this is a statement which cannot happen. So it can't be true and false at the same point in time. So this is the impossible event. This is P of false. This cannot be. And in here we say the probability that A is true or A is false. So just these two options can be true or false. And the probability that A is true or A is false is always the case. So it's P of true. So we can replace this by P of true and this by P of false. So the next step will look like this. The probability of true is the probability of A plus the probability of not A minus the probability of false. And then we have derived before the probability of false is 0 and the probability of true is 1. So we can replace this by a 1 and this by a 0. And then our equation says 1 equals probability of A plus probability of not A. So what we can do is we can just move this 1 over here and move the P of not A to the other side, multiply the equations by -1, and then we get our final equation that the probability of not A is 1 minus the probability of A. Okay? So based on those axioms, we have derived here what the negation of a probability looks like. So what not A looks like, given that we know what P of A is. And similar to this example over here, we can use those axioms to derive different statements. We don't dive further into the details, but I just want to show you that basically everything in probability theory is follows from those axioms. And we can use those axioms to derive all the different quantities and build up everything step by step on each other. Given if you want to do everything from scratch that we are going to use here in this course, this would be a longer endeavor. Therefore, I now just kind of will fast forward and will very informally introduce the different rules that we will be using in this course in order to derive, for example, the base filter later on. Okay, so let's say X denotes a random variable. So a variable which can take different values. And if you write like this, so how we denote it here is the random variable X can take the values X1, X2, X3, X4, and so on until Xn. It's a countable number of possible outcomes. So, and then we say P of X equals Xi is kind of what is the probability that the random variable X takes the value Xi. We just use it as a kind of a sloppy notation we write just this as P of xi. So this means nothing else than this over here, that x equals xi. In 99.9% of the case, I will use this notation. Sometimes I will use this one just to make things clearer, but typically we write it like this. And so this is the probability that the random variable x takes the value xi. And P of p, the function p, is called a probability function or probability mass function. And this holds for discrete random variables. That means random variables of that form, which take a countable number of possible values. And this is what we call a discrete random variable and the associated probability mass function to it. And this function takes values between 0 and 1 because if you have whatever n possible outcomes, all the n outcomes have a probability which is smaller or equal to 1, but in sum it must sum up to 1 because in one of those events must take place, so in sum the probabilities must be 1. So this is different if we have a continuous variable, so a variable which can take continuous values. If we have a variable which can take continuous values, then we still can write in a similar way. We say P of xi equals x, or in short form P of x, is a so-called probability density function. And the probability density function is not really a mass function, and it can take values, for example, which are larger than 1. The important thing in here is that we need to integrate over this function in order to get the probability that the variable lies within an interval. And so the integral over the whole density function, again, is 1, but not the function values of this density function. So if you want to say what's the probability that x lies within the interval a and b, what we need to do is we need to integrate over our density function from a to b, and basically collect all the probability mass that lies within this interval, and this probability mass that we collect gives me then the probability that the event or that the variable x takes values between a and b. And this P of x can take different forms. This can be a normal distribution, it's the most prominent one, but can also take any other form. The important thing in here is the integral over this function must be 1. And this is kind of one of the first important things, which holds for discrete as well as for continuous functions that we have in here. So the sum over all events must be 1 because one event must be true. So if I sum up all the probabilities, we must end up with 1. In the continuous case, it is the equivalent is the integral over my density function, and the integral over my density function must be 1. And if I'm not integrating over the whole space of values which x can take, just a subset, then it's just the probability that x lies in this subset. Similar to the discrete case, if I'm not summing about over all values xi, just a subset, then I get the probability that the random variable capital X takes this subset of values. Okay? So what we can do is we can also combine multiple random variables with each other. And this can lead us to things like joint or conditional probabilities. So if we want to express that we have two random variables, a random variable x and a random variable y, and we want to say what the probability that x takes the value small x and y takes the value small y. And so this is, again, it's short form. We write as P of x comma y. So this is probably the random variable x will take lowercase x, and the random variable y takes the value lowercase y. If we have this joint, then we say the random variables x and y are independent of each other if the following equation holds. So if P of x and y equals to P of x times P of y. If this is the case, the variables x and y are independent of each other. So the probability that a certain outcome happens in x, for example, is independent from the random variable y. So no matter what y looks like, it doesn't change the probability distribution over x. This is basically what this independence means. And this is the definition of independence. So x and y are independent if this holds. And then we have the conditional probability. This is something which is typically written like this. So this is we read this P of x given y. So this horizontal bias reads as given. So this means nothing else that what the probability distribution over x, and only over x, not over y, over x, given we know which value y takes. So given we know how y looks like, this is the probability distribution over x. And therefore it's called the probability distribution of x given y. And so what holds is that how we can write this is that P of x and y is P of x given y times P of y. So it basically means so the probability of the joint, so that x and y holds, is that the probability that y holds without anything else, and then the probability that afterwards basically that x holds given that y holds. And this is the definition of the conditional probability, and we can swap those things around and we'll have exactly the same setup. So P of x given y is P of the joint divided by P of y. And of course we can do the same thing the other way around. So we can also write P of x and y are independent if holds P of x given y is equal to P of x. That means no matter what y looks like, the probability distribution is the same. So y doesn't have any impact on x. If I know y, this doesn't help me in order to say anything about x. Okay, so that's the joint and conditional probability. Conditional and joint probabilities will pop up all the time, so make sure you understand what this means, given. Okay? So the next thing I want to look into is the law of total probability. So what the law of total probability basically tells me is that if I have, if I sum over all outcomes of y, so all possible outcomes of y, of P of x given y times P of y, this is equal to P of x. Okay, so see in the following way. Y can take different values. Let's say y can take the values 1, 2, 3, just for as an example. So we can say, okay, we sum over all those values, so we try y equals 1, y equals 2, y equals 3. We say, what the probability that y actually takes the value of 1, and then say, what the probability of x given that y equals to 1. So we have the conditional probability times the probability that y actually takes this value of 1. And then we do the same thing for y equals 2 and y equals 3. And we sum up all those values. That basically means we sum over all values and only x remains. And the same holds for the continuous case, except that the sum is replaced by an integral, and I'm integrating over all outcomes of y. Okay? Very related to this, or combined with the previous rule and the law of total probability, we can get the so-called marginalization rule. What marginalization means, if I have the joint probability about variables x and y, and I sum over all outcomes of y, and sum up those probabilities, then P of x remains. So that means if I have two variables, x and y, and I only know the joint, so for all combinations of x and y, I know what the probability looks like. Then I can compute the probability only about x without y by simply iterating over all values of y and summing up the probabilities of the joint. And that's what the marginalization tells me. So if I have the joint, I can marginalize out the variable y so that in the remaining distribution, y is not there anymore. I can get rid of y by summing over all possible outcomes. Again, summing or integrating over, depending if I'm in the discrete case or in the continuous case. Okay, let's have a look to a small example to visualization. So what we have in here is let's say a small grid, and this is the x dimension, this is the y dimension, so y can take values 1 and 2, and x can take whatever the values 1, 2, 3, 4, 5, 6, 7, 8, 9 in this example. So we have 18 possible outcomes, and let's say we count how often a certain outcome actually happens. And these are these blue dots over here. So this event x equals 1 and y equals 1 has happened 1, 2, 3 times over all the number of dots that you see in here. Okay, so basically what we have basically counts for all of these outcomes. And this is basically a joint distribution. You count the number of outcomes here, 3, divided by the overall number of blue dots. This is basically a joint probability distribution. What you now can do is, you can, for example, marginalize out x. So you want to get rid of x, you only want to know how often what the probability for y equals 1, the probability for y equals 2. What you can do is now you can simply sum over all possible outcomes of x of the joint. So that means you count all the dots which fall into this bin. You're basically merging all these bins into one bin, and you're merging all those bins into a second bin. And then you count all the blue dots which fall into this lower bin over here, which gives you this value, and you count the number of blue dots which fall into this kind of merged bin over here, which gives you this probability over here. So this is then the probability P of y by marginalizing out x. And what we can do for marginalizing out x, we can also, instead of that, marginalize out y, then we would get this distribution. So here we are summing up all dots and irrespectively of the value of y. So we sum up, we basically merge those two grids, those two grids, those two cells, and so on and so forth. So this would give 3, this would be 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, this value, and so on and so forth. So this is the probability distribution over x, marginalizing out y. We can also express the conditional probability, so P of x given y equal 1, by ignoring those, because I know y equals 1, so this is given. I know y equals 1, so I know I'm in this case over here. This can be completely ignored. And then I'm just building the histogram out of those blue dots, which are sitting here with my 9 bins. So this is an example for the conditional and the marginalized probability distributions that we can see. Okay, let's go take another concrete example. Again, one of those famous examples you find a lot of books. We have two variables, M and S, which can be true or false. So for example, male and not male, smoker and non-smoker. And you want to make a probability distribution or model the probability distribution if people are smoking and put that into relation if they're male or female. Okay, so what do we have in here? We have 20 male smokers, we have 20 female smokers, we have 35 non-smoking males, and we have 45 non-smoking females. This is kind of my population of in some 120 people. So what I can do now is I can sum the counts over the different columns over here. So if I sum up those values, I will get 40. If I sum up those two, I will get 80. And this is once the number of smokers versus the number of non-smokers. So we have out of this 120 people, 40 people smoke and 80 people do not smoke. And I can do the same at the bottom here over the rows. Then it would be that we have 20 plus 35 males and 20 plus 45 females. So 55 males and 65 females, which also add up to 120 people. Okay, so this is my joint probability distribution, or actually the table of occurrences from which I can now compute my joint. So we can compute all the combinations, the probability for all those combinations. So for example, P of M and S. So that it's the person is a male and a smoker. What's the probability for that? The probability that the person is a male and a smoker are actually, out of my population here, 20 people out of 120. So it's 20, the cell over here, divided by 120. Okay, we can do the next thing. What's the probability of male and being a non-smoker? This again is, we have 35 male non-smoking out of 120, so it's 35 divided by 120. It basically means if I have this population of people there and I just close my eyes and randomly draw out people, how likely it is that they are male and that they are non-smokers. And the probability for that is 35 divided by 120. And we can do this for all the individual cells. But based on this table, we can also go a step further and derive other quantities, the marginalized distributions. So for example, what's the probability of randomly drawing a male from this population? So male are those over here. So it's basically 20 over 120 plus 35 over 120, or which is equal to 55 over 120. So 55 out of this 120 people are male. So the probability of selecting a male, if I do that randomly with basically closed eyes is 55 divided by 120. And equivalent to that, we can do this for the females, of course, as well. Here we have a larger number of females, 10 more. So it's not 55 by 120, but 65 divided by 120. We can do the same thing, of course, also for the smokers. What's the probability that a random person is a smoker? This would be 40 divided by 120. So we can actually write down those values and just compute the ratios and then get my marginalized values over here. And we can also compute the conditional probability. So what's the probability of a male given that it is a smoker? And here you need to be a bit more careful. So it means given smoker. That means we know the person is smoking. That means we are over here. This information is completely irrelevant to me right now because I know already the person is a smoker. I don't know if it's male or female, but I know the person is smoking. So the non-smokers can be completely ignored over here. So I'm only interested in this first row of my table over here. So given I know it's a smoker, I only consider this row over here, and the probability for it being male is basically 20 divided by 40. Not 120, only 40, because I know the person is a smoker. So this will then lead to the P of M and S, so this is what we had over here. 20 divided by 120 divided by the probability that the person is a smoker, which is 40 divided by 120. So if 20 by 120 divided by 40 by 120 is exactly the 20 divided by 40 that I was indicating here. So it's a 50% chance. If I know the person is smoking, it's a 50% chance to say it's a male or a female in this example. Okay, so these were examples for those joint probability distribution, the probability distribution over the individual variables, and the conditional distribution. And it's very important to understand what that means if you say, for example, P of X given Y. It's very important. So make sure you truly understand what it means and you also know what independence means. Because that's a concept that we will need now when we derive Bayes' rule. So Bayes' rule can be very easily derived. I just have those two rules that we have seen before. So P of X and Y is nothing else than P of X given Y times P of Y. Okay, so again, the joint distribution is the conditional distribution times the probability distribution over the individual variable, which was given over here in the first part. And we can do the same thing, of course, by swapping X and Y, because P of X and Y is the same as P of Y and X. And so we can derive, we can use a definition to write this one down. And so those things are the same, so it means that those two equations are the same. And if those two equations are the same, I can put this one on the other side of the equation and then divide by one of the distributions, for example, P of Y. So I can say P of X given Y is equal to P of Y given X times P of X divided by P of Y. And that's all what Bayes' rule is about. So Bayes' rule tells me P of X given Y is P of Y given X times P of X divided by P of Y. What we can do with Bayes' rule is we can, if we have such a distribution, we can use it in order to swap those two quantities. Sometimes I want to estimate X and I know Y, then everything is good. But sometimes it's the other way around. I know Y given X, but I want to have X given Y. And then I can use Bayes' rule, assuming I know these other distributions over here, in order to compute the distribution I actually want to compute. And so this is a very powerful tool that we will use very often in a lot of derivations. And therefore the Bayes filter is called the Bayes filter because it uses Bayes' rule as a key ingredient in its derivation. And so this term here is often also called the likelihood. This term is often called the prior, and this term is often called the evidence. So we see a likelihood times prior divided by evidence. And one important thing is we can use Bayes' rule also if we have what is also called background knowledge, so additional information. So if I add an additional information, let's say another variable z, and I add them to all probability distributions, additional knowledge, then the same thing holds as well. So Bayes' rule with background knowledge, so this is the regular Bayes' rule, and this is Bayes' rule with background knowledge. So basically we add an additional variable to all different distributions over here, and still the same holds. And something we call background knowledge z used in here. Okay, so knowing Bayes' rule is very, very important because we will actually use this very often. You just have to learn it, know it by heart. There's no excuse for not knowing Bayes' rule. So the next thing I want to look into is what is so-called the conditional independence. So it combines the conditional distributions and independence that we had talked before. And we say that two variables are conditionally independent if they are independent if additional information is available, so-called background knowledge. So for example, if we have a joint distribution over x and y giving some extra knowledge z, and I can say this is equal to p of x given z times p of y given z. That means those two variables x and y are conditionally independent given z, but only if z is available. If z is not available, I can't say anything about them. Maybe they are, maybe they are not, but it doesn't imply it. So this is what we call a conditional independence. Conditional independence. It's conditioned on the fact that we know z. Okay? So this conditional independence means nothing else that p of x given y is the same of p of x given y and z and y. Sorry. So if I have the background knowledge and the conditional independence holds, then knowing y doesn't tell me anything about x. So given I know z, I have enough information to estimate my probability distribution over x, and the knowledge of y doesn't help me to say anything further about x. And the same the other way around. If I know z, I have my probability distribution about y, and adding the knowledge how x looks like doesn't help me at all. And this is a different way for phrasing the conditional independence. But the important thing, which you need to take into account, this does not imply independence, or also called marginal independence, if you want to distinguish explicitly the conditional independence from the regular independence, you can call it marginal independence. So that does not mean p of x and y is p of x times p of y. It only holds if we have that background information. It may hold, but it doesn't imply that. That's kind of important to note. If we are working with our probability distributions, we often have discrete probability distributions, which we can easily represent, for example, using a histogram, just based on those counts. What's the example that I've shown before? So if I go 2 slides or a few slides back, okay, a bit longer, sorry for that. So these were our histograms. This is a way for storing a discrete probability distribution in an easy way. So that's how this is often done. If we are living in a continuous world, we have to provide often a parametric function in order to describe a probability distribution. And how are we doing this? A very popular choice is the so-called normal distribution, or Gaussian distribution. This can be a distribution which is one-dimensional, can be also multi-dimensional. So in this case, it shows the one-dimensional Gaussian distribution. It has a mean and a standard deviation, so mu and sigma. And the mean tells you where is that peak of this distribution, and the standard deviation basically tells you the width of this distribution over here. So the smaller the standard deviation, the more narrow this distribution gets, and the higher those values. So the more peaked the distribution is, the smaller the uncertainty of that distribution. And we can write the unimodal, or it's always unimodal, but we can describe the one-dimensional Gaussian distribution with this equation over here. So we have, the question is how far is my variable away from the x, a squared value divided by the standard deviation squared, multiplied with minus 0.5, put into an exponential function, and then have a constant over here which makes sure the integral sums up to 1, or integrates up to 1. We can do this also in multiple dimensions, and multiple dimensions can be 3-dimensional, 2-dimensional, 4-dimensional, 5-dimensional, infinite dimensional. Then we typically use this form of writing things down. It's very similar to the first case, except that we now use vectors and matrices in order to specify this. So this is an illustration of a 2-dimensional Gaussian distribution, and in 3D it gets harder to visualize. So we typically visualize those isosurfaces of the uncertainty. Basically, this is a surface which takes the same probability value every point on that surface. And the more you go to the inside of this ellipse, or ellipsoid, the higher the probability, the further you go to the outside, the smaller the probability. But that's something which is very hard to visualize here in this 2D world. What we can also do is we can combine multiple Gaussian distributions. So if you need to represent multiple modes, for example, we can do this by combining multiples of those Gaussians. And this is what we call a Gaussian mixture or a sum of Gaussian. In this case, we have a sum over k components. So we have basically k Gaussian distributions, and we just sum up those distributions. Make sure we normalize them so that they sum up to 1, so that the integral is 1 and it's still a probability distribution. So by using 3 Gaussians, this Gaussian over here, a second Gaussian over here, and a third Gaussian over here, we can represent this red function over here. We can do this in 1D, we can do this in multiple dimensions. So for example, here with 3 two-dimensional Gaussian distributions, and this is kind of my isosurfaces, and this is a 3D visualization of this distribution. And that is something that we are frequently using in order to represent distributions with more than one mode. It's not always easy because this sum can be tricky, for example, in certain state estimation problems or least squares problems, because it will be hard to compute the log likelihood, or the log likelihood is much more complex than in the unimodal case. Therefore, it's not always a great solution, but it's kind of the easiest solution that we typically have when we have a multimodal distribution, is to use a Gaussian mixture model. So kind of to sum up this first part over here, what we have looked into is that probability theory is an essential tool that we use to solve a lot of state estimation problems. And what these first 40 minutes here, what we have done so far was to kind of introduce what does a probability mean, what is uncertainty, what is Bayes' rule, what is conditional independence, what is independence in general, how to compute basic probabilities, at least for the discrete case, what is marginalization, what is the law of total probability, probability distributions must sum up to 1. So these are some basic knowledge that you will need on a regular basis in order to to deal with those probabilities, and in order to understand how to manipulate those distributions, what are the underlying assumptions, and for example, also Bayes' rule is one of the key concepts that we will use now in the next part of the course in order to derive a recursive, so-called Bayes filter, a recursive state estimation technique. Thank you.